Hello everyone from Math 2000, Linear Algebra. It's Professor Wenson here again with a video on your ZyBooks Section 3.1, an Introduction to Vectors. And Chapter 3 is all about these things called vectors, and we're going to see vectors for basically the rest of the course. All right, so if you get down to the Chapter 3 Introduction to Vectors, hopefully that'll set you up for success later in the semester. Alright, so here it is. Now again, I'm not going to read everything to you, and I'm not going to do all the activities. I'll just start things off and hopefully show you enough to be able to guide you through. Alright, so they have the summary here. I'll let you read that on your own. Little photo and what the objectives. Use vector notation. Find a position vector given an initial and terminal point. Find the magnitude or length of a vector. Find the direction of a vector in R2. All right, R2 is just the plain old, XY coordinate plane. All right, so I'll read the definitions at least. So vectors. A vector is a mathematical object with magnitude and direction, typically represented by an arrow. The point at which the vector starts is the initial point, and the point at which the vector ends is the terminal point, or it's like beginning point, end point. The direction of a vector is indicated by the arrow head. Right? And I'll draw arrows here in a minute. And you'll also see pictures of arrows on the animations and whatnot coming up. The most common notation for a vector is a lowercase bold-faced letter. Now, when I write them on my paper, I'll be using the arrow above notation here. But throughout this text, the ZyBooks text, if you notice any lowercase bold-faced letter, it'll represent a vector. Or as a directed line segment, such as AB with an arrow overhead, and this is the arrow overhead is what I'm going to be writing when I write my vector notation on paper. Where A is the initial point and B is the terminal point. A vector with the origin as its initial point is said to be in standard position and is called a position vector. Any vector in standard position can be uniquely identified by its terminal point. A vector is given by an n-tuple, which you know what those are, having looked at systems of equations now, but the notation for a vector as opposed to a solution to a system, that'd be a little different, but it'll still be like a matrix, kinda. An n-tuple is an ordered list of real numbers. You've seen ordered pairs, ordered triples, and so on. But here, they're going to list them with, if it's a vector, specifically a vector. In this book, they're going to use the square brackets, the rectangular brackets on the outsides. So you see the brackets and then the 2, 3 inside, and then the brackets, and then -1, 5, 7. So if you see these brackets on the outside with a list of numbers with commas between them, this is vectors. All right, this will be representing a vector with so many components. Each number inside, or each vi in the vector v1 through vn, like this, each individual number is called a component of the vector. So you have this vector here with the -1, 5, and 7 has 3 components. First component, -1, second component, 5, third component, 7. This vector with the 2, 3 has 2 components, and so on. Right? The 0 vector denoted by a bold 0, right? 0, but it's emboldened, is the n tuple in which all components are the number 0, right? So kind of like a 0 matrix, right? Every entry, every component is 0. And as I mentioned up top, the set of all n tuples in Rn, right, this is where you have n coordinates or n components, and every component is a real number. The set Rn can either be seen as a set of n vectors or the set of coordinates with parentheses, but usually you see these brackets in this book, it'll represent a vector. Alright, so I'll show you real quick how to graph a vector. I'll do these by hand as well, and you can watch the animation. But I'm going to go to a piece of paper and show you how to graph these by hand as well. Alright, so the first example on the activity is this vector. Now notice again I use this little like half arrow notation. So if you see this on my paper, I got a letter with an arrow, a little half arrow above it. This is vector V, vector V, and then I'm gonna use the same notation they have. You see the little rectangular brackets on the outside. So you have the first component, -4, second component, 3, and this is a vector in what's called R2, right? It's got two components, right? -4 and 3, and each one of them is a real number. Right. Now R2 can be represented. It's only got 2 dimensions. Right? We'll talk much more about dimension in a later chapter. But you've seen R2 plenty. It's just the XY plane. You got the horizontal axis or the x-axis, and then the vertical axis. That's actually a terrible drawing, but this should be 90 degrees here. The y-axis, right. And what we have here. Now you could also see this might also be called the x1 axis and the x2 axis, just because there's 2 axes. So in your vectors, the first component I'll call is the x1 component, or just the x component, and the second component is the x2 component, or the y component. And all they tell you is how to move. How do you move on the coordinate plane? Now if I start from the origin, right, remember if I start from the origin, this will be called a position vector, because it'll simply point to the position, the point -4, 3 in the coordinate plane here. So I could start, I could have my initial point be the origin, right, and notice the parentheses is the point 0, 0, and then have this be my initial point, right, initial. And this vector is telling me to move, to the left 4. The x1 component means move in the direction of the x1 axis, or the x-axis, left or right. So I move left 4, and then the second component is the x2 component, or the y component. It tells me move move parallel to the y-axis. And positive is up, negative is down. So this is +3, left 4, up 3. So if I start here, move left 4, up 3, I end here. And there's the point with parentheses, the point, -4, 3. And then I'll draw a little arrow, initial point to the terminal point. And I guess I should have written that. That's the terminal point. And here is vector v that I've just drawn, this arrow describing the motion, right, showing the motion from point 0, 0 to the point -4, 3. Now let me tell you something about this. This isn't, you don't have to draw a vector in standard position. A vector doesn't have to start from the origin. I could start this vector anywhere I want. So how about over here? How about at the point 5, 1? Right. Let's say the point 5, 1 was my initial point. Say that was the initial point. And then I travel from there along the vector v. I use motion vector v here and go left 4. So left 4 and then up 3. If I do that, if I go left 4 and then up 3, I'm going to land here, and that's the point 1, 4. All right, with again, parentheses are around points, and the brackets will be around vectors or motions. And this is the same vector. Now this is a hand drawing, so but they should be parallel, right? They're the same vector point. They're the same motion. So you can start a vector anywhere and end it anywhere. It's just, wherever you draw it, though, it's got to be the same motion. Both of these vector v's I've drawn are left 4, up 3, left 4, up 3. All right, so, but again, if the initial point is the origin, then this vector is said to be in standard position, and it is called a position vector. This one over here that starts at the point 5, 1 is the same vector, the same exact vector. It's just not starting at the origin. That's the only difference. Okay. All right, and then they draw a 3D one as well. All right, so here's that vector -4, 3 drawn in standard position, and then they draw a 3-dimensional one here as well, and I'll show you that as well. How would we do this? Right, now notice there's, this is R3, right? There are 3 components where each component's a real number. I'd call this R3. Now they have their X1 axis going this way, their X2 axis going that way, and their X3 axis going up. So this vector W here is telling me go 2 units in the X1 direction, -3 units or back 3 units in the X2 direction, and +6 units in the X3 direction. So again, I'm going to go to some paper and show you how I was taught, that the orientation I'm going to do for my X1, X2, and X3 or X, Y, and Z axes is a little different than what they have here. Okay, so this is a vector W with these 3 components, right? And again, this is a vector in what's called R3. Right? Again, that just tells me 3 components, and each component is a real number. Now R3, I like the way I was taught is to draw it like this. So you have kind of like your vertical and horizontal lines here, but then you have a line coming at 45 degrees. And you're imagining that this one's coming out of the page, right? Because 3-dimensional space, a piece of paper is only 2-dimensional space. You have a left, right, and an up, down, but you don't have a forward, back. Here we have a forward, back. So I've got 3 axes, right? And this will be the x-axis or the x1 axis. This one's the y-axis or the x2 axis, and this one's the z-axis or x3. And then continuing these on, I'll do it. That's going behind the paper. This is just the negative side. I'll dot for the negatives, and then x3 axis, the negative part of the axis, I'll dot, and then the x2 axis, that's the positive axis, is solid, and the part of the number line with negative numbers, I'll dot. All right, so this is the x, y, z, or x1, x2, x3, are 3-dimensional space. All right, and these are just number lines. Again, the solid parts are positive, the dotted parts are negative. All right. And then the vector here is telling me how to move. Now, as before, I'm going to do it. I'm going to draw this vector in standard position. I'm going to have it start from the origin, the point, right? So in parentheses here, 0, 0, 0, that'll be my initial point, right? I'll put initial next to that. Now again, you can have it start anywhere you want. It's just, especially in 3 dimensions, it'll be kind of ugly to put it in some other position. Now, this first component is the x1 component. This second component will be the x2 component, and the third component will be the x3 component. And it tells me how to move from my initial point. All right, so if my initial point is the origin, this is saying move 2 units in the x1 direction. So that's the one here coming out of the page. So 1 unit, 2 units. Right, so I move 2 units in the x1 direction. Right, you can't see it because it's on that solid axis. All right, then move -3 units in the x2 direction. Again, I'm going to make my notches so they're parallel to the x1 axis. All right. So here's again the negative side: -1, negative, probably not great, -2, -3. Right. So I went 2 units in the x1 direction, and then 3 units backwards, in the x2 direction, and make sure that I'm doing things parallel to the axis. So there's 2 units in the x1 direction, 3 units or -3 units in the x2 direction. So I'm here now on the x1, x2 plane, and then I'm going to move up and down 6 units. I'm going 6 units in the x3 direction. I'm going to make my notches here parallel to the x1 axis. So 1, 2, 3, 4, 5, 6. 6 units up. Right. And really, just kind of do this little diagonal here, and then we're going 6 units straight up parallel. I want parallel to that. And it's it's difficult to draw in 3 dimensions here. There we go. There it is. So this is 2 units in the x1, -3 units in the x2 direction, and 6 units up. We're creating parallelograms all over the place. And there's the point, because I started from 0, 0, 0. Here's the ordered triple: 2, -3, 6. There's the terminal point, and we'll draw the vector. All right. So starting from the initial point 0, 0, 0, and then ending at this terminal point, little arrowhead, 2, -3, 6. There's vector W, right, describing that motion. Now, like I said before, you don't have to start at the origin. I could have started at any point, and I'd draw, start at some point, end at some point. As long as I have a parallel direction, the motion is the same. I could draw vector W anywhere else. All right, so back here, again, they go through the animation, and I'll let you watch that. All right, so here we're asked to fill in. I'll just do a couple of these. All right, just looking at these graphs. Now this is in R2, see the 2 axes. This is in R3. Now R4, R5, R6, you can't really picture. And you could try to draw some extra lines or whatever, but it wouldn't really be a picture of R4, R5, R6, because those are higher than 3-dimensional spaces, and you can't really picture anything that's not, that's higher than 3 dimensions. Some people might claim that they can, and they might have a nice way of doing it, but I haven't seen a good way. All right, so from R2 here, look at vector A. The initial point is at the origin, so it's one of those position vectors. And then how did this move? What's the motion of vector A? That's right 3, up 1. So the first component's 3, the second component's +1. That's this one here. Okay. Again, I'll have you look at B. And then how about vector M? Now the problem with 3 dimensions is, this vector M, that could be in line with the x1 axis, that could be in line with the x2 axis, I don't know. Or it could be some point over a plane, over the x1, x2 plane that's not in line with either of them. Because again, it's hard to picture 3-dimensional stuff on a 2-dimensional piece of paper, right? This is a 2-dimensional screen. So let's just look at the options. 0, 3, 5. So 0 in the x1 direction, then 3 in the x2 direction, and then 5 up in the x3 direction. It looks like 0, 3, 5 works. Because look at the other one, 4, 7, negative 3. That'd be 4 in the x1 direction, 7 in the x2 direction, so somewhere off here, and then negative 3, that'd be down. You'd be somewhere over here, right, if you were actually representing this on this page. So the only one that makes any sense is 0, 3, 5, based on the picture that's drawn. And I'll leave vector n to you. Alright, and then if you're given an initial point and a terminal point, so far I've been given the components of the vectors. But what if you're given just the initial point and the terminal point, the components are very easy to find. You just subtract all the initial point values from the terminal point values. So you see it's b1 minus a1, b2 minus a2 for each of the components of the vector. So it's always terminal minus initial. Always terminal minus initial. So I'll do this. You can look at the three-dimensional one. I'll draw this two-dimensional dealie up on a piece of paper, and we'll figure that out, the components out. Okay, so say I said draw a vector here, and then find the components of that vector. My initial point is the point negative 3, comma 2, right, with parentheses, it's a location on R2. My terminal point, the point where I'm ending the vector, is 1, comma 5. And I'll draw it in from initial point to the terminal point here. And I'll call this vector v or something, right? And then we say, what are the components of vector v, right? So it's a vector in this book. I'm going to do brackets. And then the first component, you just think, how far to the right did I go, or to the left? If I went to the right, that's a positive motion. If I went to the left, that'll be a negative motion. And then for the second component, I'll figure how far up or down did I go. So I went to, from the initial point, I would go right this many units. And then for the second component, up this many units, right? That's the motion being described by this picture. As I said, it's very easy to figure out these components. Just take terminal minus initial. So what's, for the first component, what's the x1 coordinate of the terminal point minus the x1 coordinate of the initial point? 1 minus negative 3, which would be 4, right? This is 4 units right. I went from negative 3 to positive 1. That's positive, a change of positive 4. And then terminal minus initial for the second component, the second coordinate's 5 minus 2. Always terminal minus initial. Right? So that's up 3, right? From 2 to 5. So I went right 4, up 3. So the components of this vector are positive 4, positive 3. Telling me moving right 4, up 3. And what they did in the activity as well is draw that in standard position. Right? Here's the vector 4, 3 up here. But if you were asked to draw it in standard position, again, that means start at the origin. Right? And then go right 4. And then up 3. And if I'm starting at 0, 0, right 4, up 3, I'm ending at the point 4, 3. And here's the same vector. Right? The same exact vector should have the same length and be going in a parallel direction, pointing in the same direction. Now again, this is a hand drawing, so they probably don't look the same length, but they should be the same length and parallel. If they are the same vector, they're describing the same exact motion, going right 4 and up 3 units. Right? But it's very easy to find the components. Just take terminal coordinate minus initial coordinate. Okay, and they do the same thing for R3, right? So they give you, the initial point, the terminal point of some 3D vector, and for the coordinates of that vector, or the components of that vector, I do 0 minus 2, negative 2, negative 3 minus 1, negative 4, and then 0 minus 2, negative 2, negative 3 minus 1, negative 4. 4 minus 3, positive 1. Very, very simple to find the components of a vector if you know the initial point and the terminal point. So that's what they're doing here in the activities. So I'll just do this first one. A vector v with initial point negative 7, 4 and terminal point 0, 2 has what components? All right, so again, you do terminal minus initial. So you see that 2 minus 4 for the second coordinates gives me the second component. 2 minus 4 is negative 2. They already wrote that. I'm just writing the first component. 0 minus negative 7. 0 minus negative 7 be 0 plus 7, or just 7, positive 7 there. Okay. Again, they draw little pictures and whatnot. You know, they draw the vector here, and then they draw it again, the same vector, but in standard position, right, starting from the origin. And I'll leave that second one to you. All right. So our challenge activity for this is just, here's the initial, a vector has the given initial and terminal points. What is the corresponding position vector, right? What are the components of the vector? 0, 0 to negative 1, negative 5. Well, that'd just be simply negative 1, negative 5, right? If you're starting from the origin, it's a position vector. It's a vector in standard position. Whatever the terminal point is, those will be the components of the vector. Very simple, that one. I'll do a couple of these. Same deal. All right, this would just be simply, if your initial point is 0, 0, 0, whatever point you land at, whatever point the vector ends at, will give me the components. 4, negative 3, negative 5. And so that was another pretty easy one. Let's take a look at what this third one looks like. Yeah, so here's different. So again, terminal, so at 5, negative 1, right, for the components of the vector. Just terminal minus initial. Right, and you can draw them if you want, but I'll leave that to you. All right, so next part of this section is on the magnitude of a vector or the length of a vector. And again, if you remember how to find the distance between 2 points from back in maybe algebra class, that'll make this pretty easy. The magnitude of a vector is denoted by, now it looks like a double absolute value symbol, like 2 bars on both sides of the vector. That means the magnitude of the vector, and later it's going to mean something else, something called the norm. But just for right now, know that this means the magnitude of a vector is the length of the vector v. So in R2, and they draw a little picture here to show you how the Pythagorean theorem comes into play. V1 squared plus V2 squared would be the length of the vector squared. So then I take the square root. Right? So the length of a vector, the magnitude of a vector in R2 is the square root of the sums of the squares of the components. Right. And then it's just extended to R3. All right, they show you a picture here. The length of a vector in R3 is just the square root of the sums of the squares of the components. V1 squared plus V2 squared plus V3 squared. And this extends to Rn. Right? In general, the magnitude of a vector, with n components, is just the square root of the sum of the squares of the components. Right. So they give you some examples here. I'll just go to the next activity where you're actually finding more magnitude. They show you pictures and see, again, very simple. All right, so I'll do this first one. All right, I'll do this first couple. All right, so I'm finding the magnitude of A here. And so vector A has components 13, 4, negative 16. And you can draw that motion if you want in 3 dimensions or whatever. We're asked to find the magnitude or the length of this vector. How far is this motion? So again, it's very simple. Just the square root, make a big square root of the sums of the squares of the components. So 13 squared plus 4 squared plus, and then negative 16 squared. Right. So this is the square root. Now you can punch this in a calculator as well, but 13 squared is 169 plus 4 squared is 16, and then 16 squared is 256. And then adding these up, we have the square root of this sum. Now 169 plus 16 would be 185. Right, yeah, 70 and then 85, yeah, plus 256. So that's 300 plus 130, so 430 plus 11 is the square root of 441, which I believe would be 21. 21 squared is 441. Now, technically you go plus or minus, but this is a magnitude, a length, right? So this should be a positive quantity. Well, I should say non-negative, because you can have zero length. If you had the zero vector, if every component was zero, then the magnitude would be zero. But the magnitude of a vector should be a non-negative quantity, right? So you got this magnitude of A, or length of A, is 21 units. So back here, now you could have entered that into a calculator and stuff, but yeah. All right, and then I'll put up this one other vector here and do the same thing. So I've written this vector here. Now this is a vector in R6, right? There are 6 components here. Now I can't draw this, a 6-dimensional space. Can't visualize it, right? 3 dimensions is even hard to visualize on a 2-dimensional piece of paper. So 6 dimensions, and I'm not doing that. But we can still describe the magnitude of this vector. So the magnitude, or the length of vector B, again, it just extends to 6 dimensions. Just make a big square root, and it's the sum of the squares of every component of the vector. So -7 squared plus -1 squared plus 2 squared plus -1 squared plus 1 squared plus 5 squared, right? All that in the square root. The big square root. That's 49 plus 1 plus 4 plus 1 plus 1 plus 25. Okay, so I mean that's 50, 75, that's 81. Right, this is the square root of 81, which is, again, for our purposes, we're talking magnitude, we're talking length. Should be a non-negative result. That's the non-negative square root of 81 is 9. All right, so back here, enter 9. Right. Hopefully pretty easy. All right, and I'll leave CDU. The challenge is just finding the magnitude of a vector. Here we're given a vector in R2, right? 2 components. 16 plus 9 is 25, and then the square root of 25 is 5. This is a magnitude, or a length, of 5 units. And I believe all 3 of these are just what's the magnitude of a given vector. Yeah, but this one's from R3, so like 81 plus 25 plus 16, and then what's the square root of that? So I'll leave those to you. All right, then finally in this section, now this is only in R2. Right, we're only going to be talking, this last part of the section is only on the XY coordinate plane, or X1, X2 plane, 2-dimensional plane. What's a way to describe the direction of a vector? All right, so the direction of a vector in R2 only, is given by the angle the vector makes with respect to the horizontal axis, or the positive x1 axis, the positive x-axis. This angle is denoted by theta, and is found using this equation. All right, you see the little right triangle set up here? Now this is an angle this is a vector in quadrant 1 in standard position. Remember there's 1, 2, 3, and 4. This is in quadrant 1, where the x-coordinate and y-coordinate, or the first component and second component of this vector, are both positive. And if you look at the right triangle here, all right, if you think of a right triangle, you have a v1 as the horizontal length, v2 as the vertical length, and if you recall from trigonometry, the tangent of an angle in a right triangle was the opposite length, so v2, the second component, divided by the horizontal length, the adjacent length, v1. So that's where this is coming from. The tangent of theta equals v2 over v1. And then get theta alone, you take the inverse tangent of both sides. Now you gotta be careful with this. The inverse tangent of some number will only be an angle from negative 90 degrees to 90 degrees. So you're not getting an angle in that takes you that doesn't take you all the way around the coordinate plane. You know, negative 90 degrees to 90 degrees from the positive x-axis is only quadrant 1 and 4. So if your angles end in quadrant 2 or 3, then you're going to have to add something. In that case, you'd have to add 180 degrees, right? Now, if the vector lies in the fourth quadrant, I told you this will be a negative number. Remember, it'll be like from 0 to negative 90 degrees. You'll add 360, right, to take you back to the same place in quadrant 4 just to make the angle positive, right? We're going to be entering positive angle measures. If the vector lies in the second or third quadrant in standard position, then you must add 180 because, again, this inverse tangent won't give you an angle measure that ends from the positive x-axis that ends in the second or third quadrant. You'll have to add 180 if it's in quadrant 2 or 3. All right, so I'll actually go through the example they have here on paper. Okay, so what I've done, they told us we had a vector with initial point P, the point negative 8, 1, so there's negative 8, 1 in R2, and terminal point Q at negative 2, negative 5, so that's down here. So here's the vector, this arrow, P to Q, right? Initial point P, terminal point Q, a little arrow over it. There's the vector PQ. Now, when we talk about the direction, right, when they're asking you for the direction of a vector, that's what is the angle formed by that vector in standard position and the positive x-axis. All right, so I'm going to find we'll write out what this vector is, what its components are. All right, and then I'm going to put that vector in standard position. So here are the components. Now remember, it's terminal minus initial. Negative 2 minus negative 8 would be positive 6. All right, so you see that's 6 units to the right. And then negative 5 minus 1 is negative 6. So that's 6 units right, 6 units down. So I do the same thing starting from the origin. All right, so here's the point 0, 0. I'll draw this vector in standard position. Right, so 1, 2, 3, 4, 5, 6 units right, and then 6 units down. Here's the terminal point. Now again, this is by hand that I'm doing here. So this is not beautiful, but gets the job done. All right, here's the vector PQ again, right? Just drawn in some other place. Instead of starting at P and ending at Q, though, it's starting at the origin and ending at the point 6, negative 6. But it's the same vector, same motion. So when I draw that vector in standard position, when they talk about the direction, right, they want you to find the direction of the vector. That's this here. What's the angle it makes with the positive x-axis? So here's the positive x-axis. I'll make it like a little jaggedy like that. There's the positive x-axis. Now they would like that angle as a positive measure, and again, hopefully you recall from trigonometry class or whatever pre-calculus you took, an angle is a positive measure if you are going counterclockwise. So we're talking this angle here, this angle right here. Okay, so this is the angle I'm looking for. What's the angle formed by the positive x-axis and my position vector? Again, the same vector that is over here. What's the angle formed? Now, that formula they gave you, the formula of theta equals, the inverse tangent of the second component divided by the first component, that little formula. Well, the second component of this vector is negative 6. The first component of this vector is positive 6. This formula only gives you the angle formed in quadrants 1 and 2. And I'll show you what I mean. This will be the inverse tangent of negative 6 divided by 6, which is the inverse tangent of negative 1. Now, if you put this into your calculator, in degree mode, right? So I'll pull a calculator up. Now you should know this. This is actually a special value. Inverse tangent of -1 is -pi/4 radians, or -45 degrees. But say you forgot that. Now if I pull my calculator up, now make sure, now we're talking all our angles in degrees in this book right now. So make sure if I hit the mode button, this is a TI-84, 83, 84 will be similar. Make sure you're in degree mode. Alright, so when I enter the inverse tangent, which is above the tangent, that little blue here hits second, then tangent. Inverse tangent of -1, you'll see is -45. -45, degrees. This angle is right here. That's this angle here. Right, that's the angle form of the positive x-axis. Now, remember, negative angles go clockwise. So that's this angle here. Right. Okay, -45 degrees. What the formula gives me is the angle formed, I'll just say angle between the vector and the horizontal axis. So not necessarily the positive, all right, the entire thing, because you'll see later if the vector shows up over here in quadrant 2 or quadrant 3, this inverse tangent formula is going to give me an angle formed with the horizontal, and I'll show you what I mean with a picture in another example coming up. All right, so that's -45 degrees. So if I want this angle, just add 360, right? Again, they mentioned that earlier. If you're in quadrant 4 like this is, right? This is quadrant 4 here. Just add 360 degrees. Right. And if you're in quadrants 2 or 3, just take this inverse tangent and add 180. And that's all. Right. So our direction vector here, theta, is -45 plus 360. If I add 360 to -45, that's positive 315 degrees. We would say that this was the direction of the vector, 315 degrees off the around from the off the horizontal. Right. And again, that's exactly what they're going through here in this example. See the 315 they end up with there. So you got to pay attention to. I would recommend drawing a picture, right, and paying attention to the quadrants, and then using their little guide up here. If it's in the 4th quadrant, you take this inverse tangent of the 2nd component over the 1st component of the vector. If it's in the 4th quadrant, add 360. If the vector is in the 2nd or 3rd quadrant, take that same formula, add 180. All right, so let me do this one now. All right, so a vector v will be a vector with initial point 7, -3 and terminal point 4, 1. All right, so I've already popped this up here. Initial point 7, -3, terminal point 4, 1. Here's 7, -3. Here's 4, 1. There's vector v that they're talking about. Again, I'm going to draw this in standard position. So let's figure out what the components are. So vector v here, is again terminal minus initial, 4 minus 7, -3 for the first component. 1 minus -3 is 1 plus 3. That's 4 for the second component. All right. So when I draw this in standard position, starting from the origin, I go left 3, up 4. Right. So again, not perfect with the hand drawing. If you want to do graph paper, that might be a little better looking. All right, so there we go. Here is vector v again. Now notice this ends in quadrant 2. Right? This is ending in quadrant 2. So that means I'm going to take, for this theta, right, this angle, formed by the positive x-axis. Here's the positive x-axis. The angle formed, the positive angle formed, right, so going counterclockwise between the positive x-axis and the vector. I'm looking for that theta. Now notice that's more than 90 degrees but less than 180. When I do the inverse tangent thing, right, if I do the inverse tangent of the second component divided by the first, so 4 divided by -3, this is going to be a negative number, some negative angle. And then I just add 180. It's going to take me down here, All right. Again, this is going to be a negative angle, and you can see it when I do this. Right? Let me pull up the calculator again. Oh, it's already up. I do inverse tangent of, well, it's negative 4/3, right? Negative 4/3. And you see this ends up being negative 53 degrees. All right, so this gives me, this is approximately negative 53 degrees. Here's negative 53 degrees. Say around there. All right. If I draw this. Do you see how that's if I just add 180, I'll be in quadrant 2, right? Right now I'm in quadrant 4 with this negative 53 degrees. To get to quadrant 2, I just simply add 180 degrees, right, to get halfway around the coordinate plane. So that's why when you're in the same thing would happen in quadrant 3. That's why when your vector's in quadrant 2 or 3, and you take this inverse tangent of the second component divided by the first component, you're going to have to also then add 180 degrees, right? So then on my calculator, I'll just go plus 180. I get 126 degrees, or 126.86 degrees, right? And that'll be the direction. So theta is approximately, let's just round that to 127 degrees. Right? That's this here, right? This is approximately 127 degrees from the positive x-axis going counterclockwise to the vector. Okay. And that's our direction of the vector in R2. Right, so they have you draw the thing. All right, again, where are the components? Negative 3, 4. Have you draw the thing. It looks like this first option looks good. And then we saw it was about 127 degrees down here, right? Oh, what is the magnitude of vector v? All right, might as well do that as well. Right? And we found the direction, right? The direction of the vector. Remember the magnitude. I've already seen one like this. That's this like double absolute value looking thing. Maybe remember the square root. The length. It's the length of it, right? Of the sum of the squares of the components. So negative 3 squared plus 4 squared. This is just 5, right? The square root of 9 plus 16. I saw one like that earlier. And magnitude, remember, should always be non-negative. Alright, so that covers everything that you're expected to be able to do. And then you have your additional exercises, which, some of these are in your assignment 5. And some are not. I would still recommend doing all of them, though, just for extra practice. And you can also check yourself. You can reveal the solutions, see how you did. Please don't look at the solutions before you try them out. Right? Please work on the problem. Try to do it as best you can before you look at the solutions. Solutions should just help guide you, because you're not going to learn anything if you just look at the solutions first and then copy them down. Right? You're not going to take anything away from this, and then you'll do poorly on the exams I write. You won't, unless you actually go back and learn something. Right? So yeah, and that's it for section 3.1. Hopefully this video is a decent guide for you to get through it and get through the assignment problems. And if you have any questions, let me know. Thank you for watching.